Hello class, welcome to chapter 5, integration. Here we focus on the definite integral. In the previous lecture, we saw extensively on how important it is to chop down the given area into very, very thin rectangular slices so that when we add their areas together, we will eliminate overestimation, underestimation. We can reduce an area that's exact and not an approximate a value because we then have the getting instead of rectangles as opposed to finite points. And that idea we're still developing, but in the path that simple, we could apply limit to Riemann sum. So limit as n approaches infinity to the Riemann sum helped us to obtain a near perfect measure of the area under the curve. So I cannot insist enough in saying that you really zip up in that in this. These rectangles being very, very thin so that their base is almost negligible because your rectangles are like the lines. You really can't see the width for these rectangles. That's the kind of fineness with which you'll draw these rectangles. So you can only imagine this, right? And this is possible only if you had your number of rectangles going towards infinity. If you have infinite rectangles, and you may come back and say, yes, then it's possible to have these extremely thin rectangles. Therefore, when we apply limit to the to Riemann sum, and we know that Riemann sum is summation k 1 to n. You could use k or I. The book uses the k. This was the one you saw for Riemann sum. And if you remember xk with an asterisk, with a star, it tells us that you can choose any point in the interval. It doesn't have to be the left end point, the right end point, or the middle point, midpoint. It could be any point in the interval. And that's because your rectangles are so thin, it really doesn't matter where you pick your point. Yeah. All right. So this means the summation you see here for finite sums becomes the integral symbol. Remember, integral, the way we defined it was the collection of all antiderivatives. So this is all possibilities. These are all possible. So this integral symbol then becomes for infinitesimal sum. Because you're adding the areas of infinite number of rectangles. This also means that our delta x becomes dx. Again, if you recall, dx was our differential. So the differential it's basically the same thing, right? The difference between the x's. But the differential, when we use that language differential, we mean a very small change in x, a very small change, meaning the width is extremely small. And that is what we are saying here when we say our rectangles are really thin and their base, the width, is really, really small. So delta x becomes dx. And what happens to f of xk star, right? F of xk or f of ck, f of ck or f of xk minus 1 doesn't matter because this is one particular a value of a particular point on the graph, right? It's a particular point on the graph. And this could be any point on the graph. And so when you're considering every point on the graph having a rectangle passing through it, then this becomes f of x. Because this is now becoming a continuous movement. Every point on the graph has a rectangle that represents it or that passes through it. Therefore, every point is represented with a point. And this means that the width between partitions. Meaning the partition, you call this the norm, approaches 0 as the number of partitions approaches infinity. That makes sense, isn't it? The width between the partitions will pick up. So collectively, what do we see? Collectively, the limit n approaches infinity. Summation P1 f of ck delta k under delta x. I put ck, but the school becomes. So we said, you now have this whole thing. K1 to n and n goes to infinity, right? So this together is a collection of all of these rectangles. So these rectangles are constructed between a and b. So integral a to b. This becomes f of x, k star becomes f of x because it's for all values on the of the function, and delta x becomes dx. Okay, and this is the definition of definite interval. We call it definite interval because it happens over a definite interval, a to b. It's math. Going endlessly, it is a definite start and an end point over which it's over this interval that we try to find the area under the curve. And so I'll say this is the definition of definite interval. So let's once again go over the parts of the definite integral. So we're saying a to b, integral a to b. Oh, by the way, remember when we looked at this notation at first, I said it looks like an I for integral. Now, if you look at it, it looks like an S, isn't it? It looks like an S. S to indicate the sum, the Riemann sum that you saw. It's the sum of all the areas of the rectangles, and that's what it means. So it's integrating all the areas. So it's so beautiful that it's, working in every direction. The symbol works, the meaning of it works, and the derivation also fits in nicely. So I really love the very appropriate symbol here. Okay, we know that this S-like symbol is called the integral sign. And A and B, they are the limits, right? The limits, the interval. So we call them the limits of integration. I'll just say lower limit here because this is the lower value always comes down. So that's how you read it. You say integral A to B, bottom to top. Okay. So I'll say lower limit of integration. And B would be the upper limit of integration. And we know f of x is a function. It's known as the integrand, the one that you're integrating. And in all of this, you see x being played as the key information here. So this x is the variable of the integral. If it's all of these stuff, G will become the variable integration. So, all right. Now that we have kind of evolved, just like how in derivatives, limit of dq took on a new notation, either the prime notation or the dy over dx notation. Likewise, we now have integral as a new notation for limit of Riemann sum. And just as how we saw a number of rules that followed that helped us to find the derivative so quickly, right? So when we had to find the derivative of, say, x squared, we had to do the x plus h, f of x plus h minus f of x all over h. That limit of that dq is what we did to get the derivative originally, but once we got the rules, we simply did, oh, derivative of x squared is 2x. You got that just because of those rules, right? Similarly, we had rules of a simplify our process, our integration process. And we've seen this before because we did the antiderivatives. And what you're learning now is basically this integral is your area. And we'll get to that. We'll try to make the connection soon. But what we're seeing is that this is integration that can be seen as antiderivatives. That's how we were introduced to this. But now we have a definite integral wherein you have lower limit of integration, upper limit of integration, and that carries a set of rules. So let's check these rules. So these are the rules satisfied by definite intervals. Now remember I said the lower limit should always, the lower value should always be in the bottom of the integral sign, and the upper limit should be on the top, so that you say integral 0 to 1. You don't say integral 1 to 0. Just as how you would read any intervals, right? You say 2 to 3, you don't say 3 to 2. You always read from small to big. So in that sense, the order of integration is very important. And what this rule says is, if you have the order mixed up, if you went from B to A, if you went to the opposite direction, then that opposite is indicated by the negative, and where you adjust the limits properly so that the lower limit is on the bottom and the upper limit is on the top. So this order of integration rule adjusts it for you if you wrote the order incorrectly, or if the order was meant to be written that way in some circumstances, as we will see. Okay, so that's why it's very, very important that we consciously put the order in the way it should be. Zero width interval, the second one. There again, it's true that if you took the integral from a to a, f of x dx, you didn't really move, right? What is integral f of x dx? It says, well, the integral f of x dx is telling us that this is the area under the curve from a to b. So if you went from a to a, it just means you didn't go anywhere, right? So you were just standing at that point. So you really can't measure the area for a point. And that's what it means. So the area for such a point will be 0. Constant multiple, just like we saw in the summation, the finite sums rules as well. You pull out the constant because the whole thing is related to x, because x is the variable of integration. If you had any other variable, like in this case k, that is considered as a constant. So even though it appears as a letter, the letter is considered to be constant because it is not your variable of integration. Sum and difference rule works, additivity. Additivity, as you can see, if you wanted to add integral a to b f of x dx to integral b to c f of x dx, going from a to b and then b to c for that same function, that means it's as if you went all the way from a to c, and that's what the additivity rule says. Then you have the max and the min. So this is basically coming from our, in fact, we saw this roughly in average height, but I'll kind of explain that shortly. So what we have is we looked at the max and the min formula previously, and so we draw this from the. Now we also have domination. Domination is if one function is bigger than the other function, like if f of x is greater than g of x, then it means the area under the curve for f of x will also be greater than the area under the curve of g of x, which is indicated by using the integral signs. In definite integral of a to b f of x dx is greater than or equal to definite integral a to d g of x dx. I have some pictures here to kind of depict these rules. So as you can see, zero width rule or interval, you did not move from a anywhere else, so you did not really span any area, so the area is 0. Constant multiple, here's an example of how the blue graph is f of x and the yellow graph is 2 times f of x. So if you went 2 times above, the area for this, the area under the yellow curve, this whole thing, this whole, what do you say, orange shaded region, that also includes the blue. That whole region is the same as blue region times 2. Okay, that's what it means. Then we have the sum. So if you wanted to add the areas, so if this is f of x and the g of x, f of x plus g of x would be the sum of the blue and the orange, which gives you the green. Don't think the green just stops just at the yellow. The green goes all the way down. Okay, it's the area under the curve up to the x-axis. So it's all the way down. You just can't see the different colors merging here. Otherwise, it'd be confusing. And the additivity rule we saw, if you took the integral from a to b, which is the orange, and if you took the integral from b to c, which is the blue, it's the same as if you took the integral from a to c all the way into. So that's going to be orange plus blue. That's all the way. There's no break. Maximum minimum, this is somewhat like your squeeze theorem. This basically comes from that idea. Okay, so if you, and it also comes from our extreme value theorem ideas. Right? So all of these are kind of somewhere influencing it in the background. So you do have a minimum of f, the minimum point of the function. Yeah. As you can see, this is the minimum point of the function, and it's indicated here. And this is the maximum point of the function. Right? So in fact, if you see EVT, if you recall EVT, extreme value theorem, if f is continuous on a closed interval AB, okay, so that's what we have here, it's continuous in closed interval AB, then the EVT guarantees an absolute minimum and an absolute maximum. And that is what we have here. So the absolute minimum will be the lowest value, and therefore it will be a value lesser than all other f of x's. And the maximum, absolute maximum will be the highest value, the highest y value for all, among all the function values. And therefore that will be above other values. So basically, this is what we did. We said minimum value of f is less than or equal to f of x, which is less than or equal to maximum value of f, right? That was the idea of EVT. That your other values, function values, will be in between the min and the max. And so if you basically multiply by b minus a on all the three parts, you will get this. And so we can look at that derivation later when we look at one of the problems. And then domination of course says, if blue graph is above the green, the orange graph, I forgot the colors. If blue is above the orange, that means blue has more area because it's above the orange, therefore it can gather more area under the curve. And so that is domination. So if your function f of x, if the blue function happens to run above the orange function, then the area, meaning the definite integral for blue, will be a value that's greater, be an area that's greater than the definite integral for g of x. Let's take a look at some of these symbols. They are given set. And they have the following above. It says find integral 4 to 1 n over 0. That sounds a little unorthodox there when you say integral 4 to 1. But we do know that integral 4 to 1 f of x dx is not the right order. So the order of integration should be adjusted with a negative sign. So you go from negative integral 1 to 4 f of x dx. And then we come back here. In fact, they give us the answers for those integrals. They don't give us the function, they give us the value itself. So 1 to 4 f of x dx is negative 2. So that's negative times negative 2. The same information. Now we have the second question. Find integral negative 1 to 2 times f of x plus 3 times h of x. Cool. So we know that we could split this into individual integers. Pull out the 2 because that's a constant. We're interested in just the variable of integration. So if it involves x, keep it in the integrand. If not, bring it outside the interval. So this is f of x, negative 1 to 1 f of x, and negative 1 to 1 h of x. Negative 1 to 1 f of x is 5, negative 1 to 1. Inside SPT. This but before says point. Negative done before s of x dx. Go back to the solution. So it's going to go negative 1 to 4. I do have 1 to 4 for f of x. And again, for f of x, I have negative 1 to 1. So then we could use the additivity property, which says you didn't go from negative 1 to 4 if you took a break at 1, right? Because that's what they have. Negative 1 to 1 and then 1 to 4. So to answer this question, I split up the interval of 1 by use 5 plus, this was a negative 2. So 5 basically 5 minus. Show that the value of integral 0 to 1 square root of power 1 plus percent x dx is less than or equal to 2. Now, when you have this inequality, I'm naturally drawn to the max-min inequality rule. The rule says, minimum of f times b minus a. The b and a are these endpoints. Is less than or equal to this given function. Max function f times e minus a, right? That's what we're told. But we are actually interested in just the right side of the inequality because we need to show that this is less than or equal to square root of 2. So then to focus on just the right side, I need to take a quick look at the graph of this. So you can use a graphing calculator or you could do it analytically by finding the critical points and use the endpoints plus the critical points, plug it in the function and find the maximum value. I just like to look at the graph, and then what I see is the graph actually, it goes on, let me just show you. The graph actually goes like this. Okay. But then we're only focusing on this interval 0 to 1. So what is the area here, right? That is what we're interested in. But right now for this this problem, we're not asked to worry about the area technically, but we're asked to focus on the maximum function value. The maximum function value actually occurs at 0. Okay, so so I say absolute max happens when x is 0. When x is 0, square root of 1 plus cosine 0. This is 1 plus cosine 0 is 1, which is square root of 2. So absolute maximum is square root of 2. b minus a is 1 minus 0, which is 1. So if I come back here and write my inequality, just the right inequality. And if I substitute maximum value, absolute maximum happens at 0 and the value is root 2 times 1, just less than or equal to the order. And hence we have proved, we have shown that the value of this integral is definite integral is less than or equal to root j. So we now formally define this definite integral that we got from the limit of Riemann's sum, because it has a very particular use as area under the graph of a non-negative function. So here's the definition, and let's read through it. If y equals f of x is non-negative and integrable, you need to find the antiderivative, right? It's integrable over a closed interval ab, then the area under the curve y equals f of x over this interval ab is the integral of f from a to b. So in other words, the area A is equal to the integral a to b f of x dx expression. Okay, this is really, really remarkable, because what we are saying is that, or in other words, how we would interpret this is that if all Riemann sums are added, they converge to a single definite integral. Because this single integral in itself contains a collection of all antiderivatives. In other words, it implies the area under the curve is nothing but, it's the same as the integral of a function of the. But I really get struck by this, because we were struggling how to find the area of an irregular shape. We write all these formulas for popular shapes or infamiliar shapes, but when it came to irregular shapes, we thought we could only do it by summation, and we did. We came very close. But now we've reached a point where we are able to give the exact value, no matter what that curve is, which is indicated by the function f of x. No matter what it is, as long as we know what interval it is that we're focusing on, what a to b is, and the function, that's it. That gives you the area, and that's the area under the curve. And we do have the premise, right? The premise is that f of x is non-negative. So that means it's a graph that is above the x-axis, and it's integrable over a closed interval. If these conditions satisfy, then your area is the definite integral. Area under the curve is a definite. So we can kind of illustrate this using a geometric shape so that we're using it. So this question says to compute integral 0 to b x dx. And we have the diagram, y equals x, of course, is the function, right? X is f of x. And so that is your that 45-degree line that splits your first quadrant in half, right? That's the line, that's your identity function. And it's 0 to b, so you're only focusing on the area under the curve from 0 to b, so that's what you get. So I have a way to prove that area of this is basically a triangle, right? So area of this triangle, so which is the area under the curve, is the same as this integral 0 to b x dx, okay? Because that's what we just showed. We kind of defined it to be that way. So let's start with what we know, which is area of the triangle. Area of a triangle is half times base times height. So it's half times base. Base is 0 to b, so it's going to be b. Height, if you plugged in b in your function, right, the height, this coordinate, will correspond to a b. So this height is also b, because that's the identity function. Whatever your x is, so is your y. That's b. So we get b squared over 2. This is what I get from geometry. Okay. Now let's focus on integral 0 to b x dx. Now we know how to find the integral of x dx, we haven't seen how to handle 0 to b, right? The limits of integration. We're getting to that. We'll look at it shortly. But we want to use the original definition, which is limit of Riemann sum. Okay, so I'm going to revert to that because for now we do not know other ways to handle this. And if you recall, we said this is a plus k times b minus a over n times b minus a over n. Remember that expanded one? This is coming in very handy because I am just using, in this case, we could say I'm using the right-hand method, the right-hand points method. Doesn't matter what method we use because we're just using the a, the k, and the b. So that's limit n approaches infinite. Summation 1 to n f of a, the starting point a is 0 plus k times b minus 0 over n. We're going to keep the n as it is. A times b is b, but a is 0. Let's clean that up. F of dk over phi times e over phi. Now, before we plug in the function, we want to remove anything that does not involve k. We could do that, but we can wait, I think, for the next step. Meaning I was hoping to move the b over n, but not yet. Okay. K is 1 to n. So I bring the b over n in the front, and I pull out the b over n from the function f of k over n. I'm sorry, I put out the n already. It says f of k. Okay. Are you with me on this? This b over n is pulled out, and this b over n is pulled out. This b over n is happening in the function. So when I pull out this b over n, I have to remember to keep it in the function. So let me quickly point to you what I did. This is what I pulled here. This is what I pulled here, so that the f comes there. So you have to rearrange it, or d squared over n squared. And what is f of k? Now this is identity function, right? F of x is x itself. So whatever x is, that is your y, basically. So if it is k, then it is k itself. F of k is equal to k. Because of the identity function. All good there. Now we will focus on the summation, and this is where I wanted to call the b squared over the limit n approaches infinity. I bring out the b squared over n squared because that's a constant, because my summation only involves k, so I don't want to really keep the b squared over n squared in there. B squared over n squared times summation k. If you recall, we saw a formula for that. It was n times n plus 1 all over 2. So that's what we use here. And one of the n's would go away. So I'm going to pull out the b squared from here and the 2 from here, because those are constants. Because now we've taken care of the summation. Now we need to take care of the limit. And as you know, the limit involves only n. So anything that does not involve n, the other constants can be pulled out. So I have n plus 1 over n. That's what we're left with for the limit. And if you recall what we did under limits, we divided by the highest degree in the denominator everywhere. So n plus 1 equal n. Do that. Oh, you're welcome. This technique, if you recall, we like this technique because this pushes the n to the denominator because of the way we choose to divide by the highest degree of the denominator. it guarantees that your n's will be eliminated or they will be brought down to the denominator. So limit n approaches infinity, 1 plus 1 over n over 1, isn't it? And then when you apply the limit, this becomes 0. So 1 plus 0 over 1, which is 1. Okay. I know you're wondering, well, didn't this take forever for us to get this? We got this like that in geometry. Well, of course, geometry is fun just because of the easy formulas we have, but that's because I gave you a familiar shape. But I also want you to see the appreciation of how we've moved from, Riemann sum and then the limit, and how we utilized older techniques of calculus, or rather, I should say, the early techniques of calculus, which is applying the limit. And I know this is lengthy, but we're going to get to the point where it's going to be so much easier. Okay. I can kind of break the surprise to you, but that I don't know if you will appreciate it. Meaning, I can show you that integral 0 to 1 dx, okay, is x squared over 2. This is how we apply the limits. Oh, this was 0 to b, isn't it? So then we plug in for x as b, and then for the 0 for x. So that comes out as b squared over 2. So we do have a very, very quick way of matching with this answer using integration. But that's a surprise I didn't want to spoil, but now I did. Note this. So what happens is we are showing you the origins of integral, and then we will show you the shortcuts to integrals. So you're not going to be doing this forever, but you will need to know how we do this. Good. And so anyway, the point I was trying to make was the area of the triangle is the same as the area of, or same as the definite integral. It's not a coincidence because we took the long way to show this, and we clearly see that this is working out perfectly as expected. Average value of continuous function. The definition says if f is integrable on AB, then its average value on AB, also called its mean, is 1 over b minus a times integral of d to b f of x. In the previous lecture, we discussed about the average value as the area over the width. And if you recall, this actually came from rearranging the formula for area, which is length times width. But we saw the length more as a height times. And so height is nothing but the value, the value where the height is attained, right? So that's the average value. So from this, if you solve for height, you will divide both sides by width, and that's how we got area over width. And then this height is nothing but the average value. So we got this information. But if you see this particular definition, it involves the integral. So let me come back to that. Average of f, which is also known as the mean, is still area over width. But now we saw that the definition for area under a curve is the definite integral a to b f of x dx over the width b minus a. So if you again, brought out the b minus a separately, that's the same as per definition. So it's not something new. It is the same information, but instead of doing the finite sums, the approximation using upper estimate, lower estimate, or the midpoint rule, instead of doing that, we now have a better way. In fact, instead of approximation, we now have an exact way, which is using the approximating. So we got. And based on this, let's look at this problem. Find the average value and f of x equals 4 minus on the Okay, now because we could do the same thing using, of course, the approximation, but of course we're not going to do that. So average a function as 1 over b minus a over c f of x dx. That's the definition. Let's plug in all the details we have. 2 minus a negative 2. Be careful there. Otherwise, we have 2 minus 2, which would be a 0 in the denominator, making it undefined. That would be totally missing. And a to b is always smaller to the higher value, and it's clearly seen in the way you write your interval. That's the same way you will write your limits of integration. And f of x is square root of 4 minus x squared. Now, once again, we haven't read this as 2 plus 2, it is 4. We haven't seen how to evaluate the integral when it has the lower and the upper limits. We know how to handle the integration by itself, maybe. We do not know how this should be done. Therefore, we're going to consider the fact that this square root of 4 minus x is nothing but a semicircle. And it's a semicircle of radius 2. How do we know that? Well, we know the equation of a circle is x squared plus y squared equals r squared, a circle with center 0, 0. R squared would be here 2 squared, which is 4. So y squared will be 4 minus x squared, and y is plus or minus square root of 4 minus x squared. Now, the positive root would be the upper semicircle, and the negative root will be the lower semicircle. Together, it forms the circle. So here we are talking about the positive root, therefore it's the upper semicircle. And of course, the integration limits also indicate to us that the radius was from, the radius is kind of negative 2 and 2, so its radius is 2 on the side versus ours. So using all these details, if you took the area, now this is this whole thing. This is the area of the upper semicircle. So the area of a circle will be, or rather I'll say, area of a semicircle, area of the circle divided by 2, isn't it? It's half of the area of the circle. Let's see, actually half times area of a circle is pi r squared. R is, radius is 2 here, 2 squared. So that's going to be, then you clean it up, you get 2 pi. And so that's what I'm going to insert in the step here. That's going to be 1 over 4 times 2 pi, because integral of that indicates that we're talking about the area of the upper semicircle. And so that's going to be pi over 3. The average of the function is we've come to the end of this particular lecture. What we do notice is we know how to find the average value of a function. The only catch is, let me take you back here. Only catch is when you have to find the integration, because we have not explored all the techniques that we can use. The various integrating and then applying the division. We are going for, in this case, geometry to help us with it. In some other cases, we go for finite sum approximation, which is kind of counterproductive to some extent, wherein you're not able to use a quicker way to get the answer. But we can still do it. It's going to be lengthy, but we can still do it. So those are the only limitations that I see as of now. But once we kind of reveal or explain all these concepts to you and shortcuts that we can use, then it'll become a breeze. Like the next lecture, it will be on the fundamental theorem of calculus. Right there, we will kind of show you how to use the limits of integration. And after that, this will become easy. For now, you'll have to use this roundabout way. But that's about it. So I really hope you enjoyed the concepts that were discussed in this lecture. I will see you in the next one.